Welcome to the course Statistical Data Analysis 2. My name is Michael Varsitulis and I am your lecturer for this course. This course is a direct continuation of what you did last semester with Professor Shravan Vasisht, namely in the course Statistical Data Analysis 1. In this first video lecture, we are first going to recap a few of the main and basic concepts regarding statistical analysis. So this is going to be a little bit of a repetition, but nonetheless it will be very useful in order to make sure that we are all on the same page before we move on to the new and exciting topics that this course has to offer. So today, in this recap lecture, as we may call it, we will revise a few of the basic ideas regarding questions like, why do we need statistics, so statistical tests and statistical models at all in linguistics and psychology? We are also going to talk about how these tests work and what the output of a statistical test means. We will also revise or refresh our knowledge on the t-test and linear regression in particular. And in the end, we'll also talk about statistical power and remind ourselves of what it is and why it matters. So, in general, why do we need statistical models in linguistics and psychology? Well, maybe we should first remind ourselves what we actually want to study and explain when we are studying linguistics or psychology. Basically, we are trying to understand the nature of cognitive phenomena. And these cognitive phenomena, like their computational neuronal implementation, happens right about here, okay? So we are basically trying to understand how the mechanism for, let's say, language comprehension or vision or emotional processing or any kind of cognitive process, how this mechanism functions and behaves, what its properties are. For example, in linguistics, we might be, or in psycholinguistics in particular, we might be interested in understanding what makes a sentence difficult to process as opposed to easy to process. And all of this is happening somewhere in here, in the brain, which we obviously don't have very good direct access to in order to understand what's happening there. So the best we can do is use certain cues, right? And these cues are usually some data that we can collect in experiments. So we can do, for example, behavioral experiments where we put participants in a room and let them, for example, read some sentences and then answer questions about them. And then we can collect some data from this procedure. So we could collect, for example, the reading times of the people, like how much time they need to process a particular sentence or like react to it, how much time they need to read or answer a question. We could also collect the data, let's say if we have comprehension questions, if we give them a couple of sentences that they have to read one by one, and then they will have to answer a question about the sentence that can have two response options, right? We can collect these response data, and that's something we can analyze later. Or we can do something more sophisticated. We can do EEG experiments or fMRI experiments that tap directly into the neurophysiological data, because they can like measure the electromagnetic activity coming from the brain, or in the case of fMRI, the bold signal, like they can basically determine where something in the brain was active while a certain task was performed, right? So that's the so-called neurophysiological data. And so these are basically our cues. We can collect all these data, but in the end, we are not just there to collect data, but we also want to use those data in order to understand what is going on, what is happening in the brain. So we are collecting data with a certain goal in mind. We're collecting data in order to eventually have this data inform our own theories about the particular cognitive phenomenon that we want to study. For example, we might have a theory about how language processing works in the mind. Let's say our theory says that the mind, the language processor, is basically a predicting machine, and it's heavily fine-tuned on the frequencies of words in context, okay? And that's why the difficulty of understanding, let's say, of processing a word, and thereby maybe also the time that is needed to process it, is heavily correlated with its conditional probability given the context. Okay, that's the so-called surprisal theory, for example. That's just one theory that we might have. We might also have different kinds of theories about different kinds of phenomena. And basically now the goal is we are collecting data, like these cues that give us some spurious insight into what is actually happening in the mind. Like, we're not dissecting the mind directly while people are reading sentences or doing any kind of cognitive task, but we only have these cues, these data that we can collect. And here is exactly where statistics comes into play, because in order to meaningfully be able to be informed by data, we have to apply statistical methods in order to be able to reliably tell what the data is actually indicating and to what extent the data is or is not supporting a particular hypothesis, which might be a part of a broader theory. That is, we may write here, data informs theories using statistics. And there are actually two ways in which statistics can be used in order to make sense of our data. First, we can use statistics in order to test hypotheses. And we can also use statistics in order to better understand the generative process that is behind our data. And so both of these ways we can use statistics, which we'll both look at also in the course of this lecture. Both of these serve the ultimate goal, of course, to further constrain the possible theories that can be true and to reject the theories that are not consistent with what the data tells us. So I just mentioned hypothesis testing. Thinking in a somewhat broader picture, we can also see how hypothesis testing is embedded within, well, what we may call the scientific method, where the scientific method is actually nothing else than this cyclic repetition of certain procedures, of certain steps that the scientific community uses in order to advance their collective knowledge about a certain phenomenon. Okay? So the scientific method starts with just the general kind of primitive first step to make observations about nature. In our case, for example, to observe how people behave cognitively in certain situations or when they are processing language, let's say. You may also observe yourself. You might observe introspectively what it feels like to you to read certain sentences. And once you have like a vague idea about the phenomenon you want to study, you can think of it really more in a more structured way as research. You can also consult previous work, maybe that other scientists have done before you, and see what kind of insights or ideas already exist that might be worth considering. And so for a specific experimental study, you might first want to extract a certain hypothesis out of this, broader corpus of knowledge that already exists, that is not yet verified, but that you maybe have a certain intuition about, either being true or false, let's say. And once you have a certain hypothesis in mind, then comes the actual experimental data gathering step. So you will construct an experiment that is designed to test this particular hypothesis that you have in mind. As we mentioned right previously, it could be like a behavioral experiment or an experiment where you measure the brain waves of a participant. And once you've collected these data, there comes statistics, so that's where we have to use a statistical test in order to make sense of what these data actually tell us, how they inform our theory, and how they might give us a hint that we should either reject or accept the hypothesis that we have constructed. And yeah, that's the point where we have to like interpret the data, and that we can only do once we have rigorously applied a statistical method to the data. And we can then share these results, like publish them, and other scientists can see them as well and judge by themselves if the reasoning and the analysis of the data is sound, and if the conclusions that you maybe have drawn hold up to scrutiny. And potentially, which is actually a very good idea, is to then try to replicate, to repeat the same experiment to see if the same result will hold up, even if you replicate the experiment again, maybe in a different, slightly different setting, or maybe it's replicated by other researchers in another part of the world. If that same result would come out, then this would really solidify the evidence that has been gathered. And more generally, so after one run of the cycle has been performed, then we have added a small bit of knowledge to the general corpus of knowledge of the scientific research on our particular field or phenomenon, and then the whole thing can start again. So then you, or maybe a new researcher, can come and examine what kind of observations already have been made in the past and previous research, and then define a hypothesis of their own, start their own experiment, which might build on what you have done but might be slightly different, and that's how the whole process repeats and repeats. And that's the way, ideally at least, how we as scientists try to collectively accumulate knowledge on our particular object of study, and by repeating this over and over again, getting more and more precise understanding of our subject matter. One small thing that I'd like to highlight at this point is that the kind of statistics that we're going to use in order to analyze our data is what's called frequentist statistics, okay? I'm just saying this because throughout your career as students and maybe researchers, you might also at some point encounter another flavor of statistics, which is called Bayesian statistics, which has somewhat different assumptions and somewhat different mathematical methods to analyze data, although the overall goal, of course, that is to inform theories and understand what data indicate about the world, that's all the same in both kinds of statistics. But here in this course, just so you're not confused, in case you see this other flavor at some point, we are going to exclusively look at frequentist statistics. Okay, it might be useful to look at a somewhat more concrete example in order to get a better idea of what hypothesis testing actually looks like. So let's say we are researchers and we have a certain hypothesis in mind, and I'm just gonna come up with some random example, okay? I'm just gonna say that the IQ of Uni Potsdam students, Uni Potsdam, is different from the IQ of the general population. That is, either it's higher or it's lower. This is just saying there's a difference. It doesn't specify which direction the difference has, okay? And let's also say that we know that the IQ of the general population is supposed to be 100. That's something that, in this example, we assume to know for a fact. So now, in order to test this hypothesis that we might have, like intuitively or just because we want to test it for the heck of it, what we have to do as a researcher now is to first construct the so-called null hypothesis. So the null hypothesis is actually kind of the opposite of what we want to show. So what we want to maybe show in the end is this, that maybe there's a difference between the IQ of Uni Potsdam students and the general population. But first we have to actually reverse our thinking and think about what we want to disprove or like reject, and that is the so-called null hypothesis. So the null hypothesis basically says no, there is no such difference of the kind that we hypothesize. Okay, so it just says basically the null hypothesis assumes that the IQ of Uni Potsdam students, on average of course, is exactly equal to the IQ of the general population on average, which is, well, 100. So how can we actually find out? How can we test if we can reject our null hypothesis or if we can't reject it? Well, let's think of the population of all the students at Uni Potsdam. So obviously I can't really draw 1,000 dots or how many students there are at this university, but let's assume that this is like the entire population of Uni Potsdam students. And now we want to conduct an experiment, like we want to administer an IQ test to some of these students and see what comes out. Now, ideally, of course, if we had the time and money and patience, we would like to test all Uni Potsdam students, like all of them, every single one of them. Then we could compute the average of these results, and this would be exactly the true average IQ of the entire student body of Uni Potsdam. Okay, but in real life, as it so often happens, we can only ever look at samples, at small subsets of a population. Okay, so let's say we are lucky enough to find, let's say, 30 Uni Potsdam students. So that's like a sample of 30 people that are willing to do our test. Okay, and now let's say that we find in this test, we do this IQ test on them, and we find a sample average of, we may say, 110, like an average score of 110 in this particular sample, randomly selected sample out of the population of Uni Potsdam students, which contained 30 subjects. Okay. Now, how meaningful is this result? We can see, like just by looking at it, like with our bare eyes, we can see that this is somewhat higher. It's 110, and the general population IQ is just 100. So does this mean that we have shown that Uni Potsdam students are in fact smarter than the general population? Or is this difference maybe just a result of randomness? That is, it could be that we just happened accidentally to pick out 30 of the, let's say, rather high IQ students, and this will of course distort our result. Maybe the overall average of the Uni Potsdam student body in terms of IQ is still exactly 100, but because of the randomness of just picking out 30 people by chance, we might have accidentally picked out exactly those that had like higher IQ, and that's why we get a result which is on average higher than the general population IQ of 100 that we know. So that's now where statistics comes into play. That's a puzzle we can solve using the t-test. And the puzzle is, how can we tell if this difference is reliable? And reliable would mean statistically significant. That is, we can reject the null hypothesis and accept our alternative hypothesis that there is in fact a difference between the IQ of Uni Potsdam students and the general population, or if it's just, as I said, the result of randomness and is not really a meaningful difference, because in the end of the day, the overall population of the Uni Potsdam body still has an IQ of 100 that is exactly the same as the general population. Another way to say this is that we imagine how the distribution of IQ scores looks like according to our null hypothesis. This null hypothesis would assume, of course, that the average IQ score in the general population is at the average value, at the mean value of 100, and also that there's a variance or the standard deviation, let's say, of 15. That describes basically how broadly spread the values of IQ are across the population. And now we are getting this particular data point. This data point is the sample average out of the sample of 30 Uni Potsdam students, and this was, recall, at 110. So let's say here is 110, and this is where our data point lies, like the sample average that we have collected and measured from the Uni Potsdam students. And now we're asking the question, how likely is it to have obtained a data point like this under the assumption that the null hypothesis is true? So how likely is it that just by chance this data point was sampled out of this distribution, which is the distribution that is true according to the null hypothesis? If we think it's likely enough, it's plausible enough that the null hypothesis may have produced this data point, then there is really no good evidence to say that in fact there is a difference and we have to reject the null hypothesis, because the null hypothesis remains quite plausible, okay? But if we in fact see that, let's say there is a very huge difference, I'll exaggerate a bit and say we get a value of 200. If we draw this here on the plot, we might find it's somewhere here maybe. And now the situation already looks a bit different, right? Intuitively, just by looking at this figure here. We see that this is like very far on the edges of this distribution. So it's quite implausible that this distribution will have generated this data point. Although it could have, like it's not impossible. In very rare instances, you might get like a huge outlier, either to the right or to the left, okay? But here the idea would be, if we, using our statistical methods that we will look at in a moment, if we use the methods and see that it is very unlikely that this data point has come about from this null hypothesis distribution, then we want to reject the null hypothesis and actually assume that this data point didn't come from this distribution, but maybe came from a somewhat different distribution, which has a mean at a higher value, okay? And this would be then the alternative hypothesis. We can also simulate the IQ distribution that we just saw in the example using R, okay? So here, as you see, I have a version of RStudio open on my computer. Here there is the console, so I can directly type R commands if I want. And let's say we want to generate random data that comes from a distribution with mean 100 and a standard deviation sigma of 15, okay, which is what's usually assumed to be the distribution of IQ scores in the general population. As you may remember from the previous statistics course, that is Statistical Data Analysis 1, there is a function in R which is called rnorm, which is used in order to generate random data from a normal distribution. And it goes like this. So it has 3 arguments. In the second argument, I'm going to start with that one, we specify the mean value from the distribution we want to sample from, so 100. The third argument is the standard deviation, in this case, as we said, 15. And the first argument, which I've still left empty, here we can specify how many values we want to sample. Now, in order to make this random data resemble our actual ideal distribution as closely as possible, we want to generate a lot of data, okay? So in this case, let's just exaggerate and say we want to sample 1 million data points from this normal distribution. That's obviously a lot of data, but our PC can do that within seconds, okay? That's not a problem. And now we want to say we generate this random data, which comes from a normal distribution with mean 100 and standard deviation 15. And we also want to visualize it as a density plot. So we can actually then see it as a density curve, as a probability density curve. And we'll also have to write plot, I believe, around this expression. And now once we press enter, we can see here on the right hand side of this window of RStudio our generated plot, which is now the plot that looks like our distribution that we have just defined. Okay, we can also zoom in a bit and look at it in a somewhat larger format. So as you can see, it's clearly a normal distribution. It has this bell curve shape, okay, with a peak at the value 100, because that's the mean. And its particular width is defined by the fact that we specified the standard deviation to be 15. If we had specified a larger standard deviation, this curve would be a bit more flat and wider. But if we had specified a smaller standard deviation, this curve would be thinner and have even a higher probability density at the peak, okay? So that's how the standard deviation modulates the shape of the normal distribution. Now, another thing we can do is we can simulate a sample of the size that we talked about previously, that is a sample of size 30, okay? So we had talked previously about us taking a sample of 30 Uni Potsdam students and then measuring their IQ score. And let's assume for a moment that the true IQ of Uni Potsdam students, of the population of Uni Potsdam students, on average is, let's say, 105, okay? So we are now going to pretend that that's the case. I'm going to simulate data from that, let's say, universe where Uni Potsdam students on average have IQ score of 105. So we can again use the rnorm function. We want a sample size of 30. So that's our first argument here. And we say the true mean is 105, so a little bit larger than the IQ of the general population, but really close. So it's going to be hard to tell from the sample if there's actually a difference or not. And let's say there is even larger variation among Uni Potsdam students than there is in the general population. So we might have a variation, a standard deviation, which represents the variation of 25, okay? And so we might maybe save this in a variable called up sample. And so we can do that. Okay, this could be maybe our first sample from the Uni Potsdam student population. So we have this, we can look at this as well. I mean, we can print it out, we'll see it's just a bunch of values. We can see the minimum value in our sample is 73, okay, it's rather low, and then the highest value is, oh sorry, I shouldn't have gone into caps lock, 155, and if we take the mean of this sample, it is 106.8. Now notice the sample mean is not exactly this number 105 that we had specified here, okay? So it will obviously vary from sample to sample, and that's what we can see if we, for example, take another sample from the Uni Potsdam population. We could just copy this code over here and run it again and call this sample 2. And we can also have a sample 3 and 4. Okay, maybe that's enough. And so each time we evaluate what the sample mean is, we'll see that it's a slightly different value. Now in this case, sample 2 has 102, okay? Sample 3 has 103, and sample 4 has 104. So it's obviously going to be close to what we specified as what's going to be the truth in our simulated population here, which is 105, but it will obviously never be exactly the sample mean that is also in the overall population because of the sampling variance. And now we can see maybe if we plot this first sample as a histogram, we can also visualize it. So this is now the distribution of IQ scores in the first sample of randomly selected 30 students. But if we had picked a different set of 30 students, we would have a sample that looks slightly different. Okay, so this is all just a result of randomness, right? So each time we sample from this distribution, we get a somewhat different looking sample with a slightly different mean and maybe a slightly different sample variance as well. Okay, but for now, let's maybe focus our attention back on the very first sample that we randomly generated, which had a sample mean of 107 roughly, sample standard deviation of 24.12 and so on, and whose histogram plot we can see here on the right hand side. So assume now this is actually our experimental sample. This is obviously all fictional, but let's say these were real Uni Potsdam students that were now tested on their IQ, and we want to know if this small difference of 6.8 IQ points that their sample average has from the general population mean, which is known, which is 100, if that is a meaningful difference or just noise. And in order to decide that, we will apply an inferential statistical test. So in order to perform this statistical test, a key concept that we will need is the so-called sampling distribution of the mean. So the sampling distribution of the mean basically describes the idea that we are repeatedly sampling again and again from the same population of interest. And each time we are sampling, we are basically grabbing out a sample of the same size. For example, we could have specified size 30, and then we would sample, let's say, this sample, and then again another sample which also has size 30, and another one, and another one, and another one, and so on forever. Okay, so this is actually not a practical idea, so it doesn't mean that we have to do this. Obviously this would take very long time and it's not feasible at all. It's more a kind of theoretical thought experiment that we have to do in order to construct this sampling distribution of the mean. So the idea goes like this. Suppose for a moment that the null hypothesis is true. Okay, so we don't know this, but if that was true, then we can imagine a distribution of the means that all of these possibly infinitely many samples that I take out of this population have. Okay, so for example, this first sample might have a sample mean of 106. Maybe this one has a sample mean, this X with the bar just means sample mean, okay? This one maybe has a sample mean of 97. This one has a sample mean of, let's say, 99. This one has a sample mean of 102. And this one has a sample mean of 110, okay? So we are gathering all of these sample means together of possibly infinitely many of these samples we have taken out of the null hypothesis distribution, for example, of IQ scores. And now, like, we're collecting them all in one bucket, you can imagine, and now we are plotting basically how their distribution looks like. So now this is not the distribution of the raw IQ scores in the general population, but instead it is now the distribution of the means of these individual samples that we have taken out of the population. And so if we assume that our true population mean of IQ scores is at 100 and our true IQ standard deviation in the population is 15, then we know from the central limit theorem, which was introduced in Statistical Data Analysis 1, that the mean of the sampling distribution of the mean should actually be also equal to mu, just the same as the population mean. But importantly, the standard deviation of this sampling distribution of the mean will now actually be sigma, which is the population standard deviation, divided by the square root of n, which is the sample size, right? So you can see that this sampling distribution of the mean will have the same average value, like the same peak as just the population distribution of IQ scores, but crucially its standard deviation, like how wide or thin it is, that is now also dependent. It's obviously dependent on the population standard deviation, but it's also dependent on which sample size I pick. So, and it kind of makes sense, right? So if I pick very large samples, for example, if I had picked not sample size 30, but sample size, let's do something crazy like 1,000. Okay, so each time I had picked 1,000 out of these, then you can imagine that these mean values will be much more accurate estimates of the actual population mean. So these will like vary much less and maybe will be something like, okay, this one is 100.1, this one is 99.9, this one could be 100.2, this one could be 99.7. So these will be very close to the real population mean. And if you would put these together in a bucket now and would draw their distribution, then you would see that it would be actually much thinner than this. It would be something like, I mean, it's hard to draw here because I've already little space, but you could imagine that this curve would look something like this, okay? So much, much thinner, okay? And this is because here we would have a much smaller standard error, which is the name of the standard deviation of the sampling distribution of the sample mean. Another case would be the situation where we have a very small sample, let's say a sample of just maybe 5 students, okay? In this case, we can expect that these sample means will fluctuate much more, okay? Because from a small sample, we can only get a very imprecise estimate most of the time of the actual mean. And in this case, we might see something like, I mean, I'm just thinking some values randomly, maybe something like 80, something like 109, then maybe 121, and then maybe 99, and then you could have something like 103, okay? So it will be a little bit more random, a little bit more all over the place. And this all over the placeness, you would then also see it if you would plot the sampling distribution of the sample mean, in the sense that here you would get a much wider curve, something like this, let's say, okay? And why is that the case? Well, because you can see here, this smaller n in the denominator would result in this standard error to be rather large, and that's represented by this wider curve here. Okay, before we move on, just remember to not forget this idea that when we're talking about standard error, what we effectively mean is the standard deviation of the sampling distribution of the sample mean, and that can be computed by taking the standard deviation divided by the square root of the sample size. Okay? So until now, I just gave you a conceptual sketch of how the sampling distribution of the mean would look like. But we can also actually draw the specific sampling distribution of the mean for our example with the IQ scores directly in R. So let's just go back to our RStudio session. I just changed the colors a little bit so that I can appear here as well. And remember that our null hypothesis says that the population mean should be 100, so we can call this mu. Our population standard deviation should be 15, okay? We call that sigma. And we also know, I'm going to write it explicitly here, that the mean of the sampling distribution of the mean should be exactly equal to the mean of the IQ scores in the population. So I'm going to write it explicitly as a new variable, so that's the mean of the sampling distribution, which is going to be equal to mu, and the standard error, which is, as I just mentioned, the standard deviation of the sampling distribution, will be, as we just saw in the mathematical equation, will be equal to the population standard deviation, sigma, divided by the square root. Square root I can do in R sqrt, that's the command to compute the square root, divided by n, where n is 30. Okay, so we directly write 30 inside here. And now we can see what sigma sample actually is. So our standard error in this case would be 2.73 something. And we can go on to actually plot this. So we can do this in a similar way in which we plotted the IQ score distribution previously. Namely, we can first generate a lot of data. Let's say again 1 million data points. So a 1 with 6 zeros for a normal distribution with mean mu sample and with the standard deviation, which is equal to our standard error here, right? Because that is the standard deviation of the sampling distribution. So sigma sample. And we want to create this as a density plot and also have to plot it with the plot function. So once we have that, we can run this command, and this, I'm going to make some space for the plot. This is how our sampling distribution of the mean looks like in this case. So we see obviously it's centered at 100, and it's obviously much thinner than the IQ score distribution itself, because the IQ score distribution itself had 15 as its standard deviation. So the curve was a bit wider, whereas this curve has 2.73 as its standard deviation, because that is the standard error which we computed here. Now, we should remember that this sampling distribution of the mean is a normal distribution, so it is a probability distribution. And what is the main property of a probability distribution? Well, it is that under its curve, if you sum up the area, that area, if you go from as far as you can to the left to as far as you can to the right, the entire area will sum up to 1, because the area represents the probability mass, okay? And likewise here, this area under the curve, if we were to sum the size of this area up altogether, going from theoretically minus infinity to infinity, what we would get as a result is 1. Now, the interesting thing is if we go back to our sample here, which was our random sample of 30 Uni Potsdam students, which had a mean IQ score of about 106.8. Like if you were to visualize this on this x-axis of the plot here, it would lie somewhere around here, right? Where my cursor is pointing right now. And the idea is that we want to see, like on this edge of the distribution, on this tail, if it is plausible to get a value as extreme as that or more extreme, okay? So we are counting this probability mass on the right, and because we are doing a two-sided test, we also count the symmetric probability mass on the other side of the curve, so about around here, okay? So we're counting, we're summing up the entire area under the curve on this tail, lower tail of the curve at the value that's as extreme as our data point, and also on the other side of the curve. And now the idea is that we sum up these areas, and the value that we get as a result, like the probability mass that is represented by the sum of this pink probability area here and this one, that will be our p-value, okay? So these two together, if we take them, they will be equal to our p-value. And the conventional threshold is that if this probability is lower than 0.05, That's just one possible convention, right? But a very typical one. Then we would interpret this as a significant result, meaning that we consider the result too unlikely to have been caused under the assumption that the null hypothesis is true. The convenient thing about R is that we can compute this kind of probability mass quite easily by applying the p-norm function. How does this work? So as you may remember from previous courses, we can type p-norm, and then we have to specify a few arguments. So we will specify what the exact value is at which we are looking. So in this case, this was the value which corresponds to our sample mean, so 106.8. So I might as well just type this again. And we want to specify what the mean of the distribution we are looking at is. So that was 100, aka the mu sample variable. And we also have to specify the standard deviation. That was our standard error, which is already pre-calculated, so sigma sample. And lastly, we have to specify a kind of special argument called lower tail, which we'll set to false. That's just meaning that if we take this cutoff, right, then usually by default this function p-norm would compute the probability to the left of that. So all this area where you see my hand kind of hovering and this, so all the area from -infinity up until that point. But we want to do the opposite, right? We want to compute the area after this, so just this tiny portion to the right, okay? So we have to specify lower tail false in order to do that. And now this command by itself would just compute the size of this area, okay? Not including this symmetric area on the other side, which we also want to include because we're doing a two-sided statistical test. But this area is just as big as that one because the curve is entirely symmetrical. So in order to get the overall p-value, in this case, we can just multiply this entire, what this term gives us by 2, okay? Thereby we take exactly the probability mass as represented by the sum of this pink piece here and that one, okay? And now if we press enter, we see the result. So in this case, our p-value turns out to be 0.012 something, which is, according to the convention, we would apply here significant because that result is indeed a value that's smaller than 0.05. The probability is less than 5%. The statistical test you just witnessed being executed is in fact called a z-test. This is not to be confused with the t-test that we are actually aiming for and we'll do next. The z-test is a simpler test, but it relies on a kind of artificial and often unrealistic assumption, namely the assumption that we already know the population standard deviation in advance, okay? So the z-test assumes that we know that this number is in fact 15 in the general population, like the standard deviation of the scores. But this is an assumption that we can rarely really have. So in this case it might be warranted because IQ scores are kind of defined to have the standard deviation of 15, but if you have other metrics, other dependent variables that you care about, most of the time when you're doing experiments you don't really know the standard deviation in the population in advance, okay? And that is the problem with the z-test, that it really relies on the assumption that we know for sure what the sigma is. Now the t-test is much more flexible, and that's what we eventually want to see here, because the t-test does not assume that you know the population standard deviation in advance, but can account for the fact that you don't know it yet. And that's why we're going to see how we can solve the same problem now, but without this assumption that we know the sigma, what sigma is basically. So let's see how we can actually conduct a t-test. First, maybe we should remind ourselves of some notational details. So on the one hand, we have things related to the population. For example, parameters like the population mean, which we denote as mu, and the population standard deviation, which we denote as sigma. And on the other hand, we have related parameters for the actual sample that we have available. And for the sample, the mean is typically denoted as x bar, like the small x with the bar on top, and the sample standard deviation is denoted as s, small s, okay? And then we also saw that from the, like based on the population parameters, we could also think about the sampling distribution of the mean, whose standard deviation is called standard error. And the standard error was nothing else than sigma divided by a sample size n. Okay, so it assumes some particular sample size and then it can give you the sampling distribution of the mean. But here the crucial detail is that this standard error is computed based on the population standard deviation, sigma, which we assume to be known. Okay, so that's the standard error, and that is like this. And for the sample, we would also be able to compute a standard error analogously, only in this case we would take the estimated standard deviation. Estimated means it's from the sample, it's not from the population. So it's not necessarily equal to the real population standard deviation. And so that we can write as s divided by square root of n, okay? And the idea is that for the z-test, we could rely on the assumption that we know the sigma, and therefore we could compute the standard error like this. But now we have to rely on just what is available to us in the sample. And that is the estimated standard deviation, which is small s. And so basically what we do then, in order to compute a t-test, first is to compute a so-called t-value, okay? And so the t-value can be obtained by, so it's the observed t-value, okay? So we're going to write t observed, OBS, and that is equal to the sample mean minus mu divided by the standard error, but this is now the estimated standard error. It's from the sample, it's not from the population, okay? So divided by s divided by square root of n, okay? And the idea is that this observed t-value will be some number, and then we will have to look this t-value up on a distribution. And now the crucial difference to the z-test is that we don't look it up on a normal distribution, but in fact we have to look it up on a so-called t-distribution, okay? So the t-distribution is also a probability distribution. It also has a curve that looks somewhat like this. So it's also a curve that has one mode, kind of similar looking to the normal distribution, but it usually has somewhat thicker edges than the corresponding normal distribution would have, okay? And then the idea is very similar as to what we saw for the z-test, so we would now take this observed t-value actually, and see where it lies on this curve. So maybe this is like possible t-values here, and our t observed is, say, about here. That's t observed. And so again, we would think of the probability area that's to the right of it, so as extreme or more extreme than this observed t-value. So I'm going to color this, fill it out. And because typically we do a two-sided test, and because we're testing two-sided hypotheses, we also will do the same thing on the other side, symmetrically, and we will consider this probability area to the left, which is just like the mirror image of that one, okay? And then again, we would take the sum of this probability area here, I hope you can see this, and this probability area here on the left. We would sum those two together. So I'm going to sum them, and then the result will be our p-value, okay? And again, we can check then if this p-value is smaller than 0.05 and so on. That would then mean we have a significant result. If it's bigger than 0.05, by convention, we'd say the result is not significant. So that's the theoretical idea. I'm not going to show you the equation for the t-distribution, but we can actually directly compute and work with t-distributions in R using certain commands, certain functions. So that's what we're going to do next in the example with the IQ scores that we saw previously. So back in our studio, let's see how we can apply the t-test to our example. What we have here is our sample of 30 students, and the only knowledge we can use now regarding population parameters is the fact that mu is 100, but we don't assume anymore that we know sigma. That's the difference. What we do know is the mean of the sample. Recall in the formula I just wrote down for the t-value, this would require us to compute the sample mean minus mu divided by the sample standard deviation divided by the square root of the sample size. Okay, so let's get these ingredients together. So we need the sample mean, we already have it there, but just to make it explicit, I'm gonna write x bar should be equal to the mean of UP sample. That's just the same thing as this 106 over there, okay? And we want S, our sample standard deviation, as a variable to make it a bit more overseeable, okay? We're gonna save that also in a new variable here. And we have the sample size, which is n, which in this case is 30, because our sample was of size 30. We could actually also get it by computing length of the sample, and that's indeed 30, okay? So we have everything ready to compute our observed t-value. So now let's write t observed is the following division. So x bar minus mu divided by, s divided by the square root of n. Okay, that's basically just writing down this formula, but using R. Okay, so that is our observed t-value. Now we can access it. We see that t observed is 1.54 or something. And so lastly, what we do is to compute the p-value, right? So before we had used the p-norm function when we were using the z-test, but keep in mind now that we have to actually use a t-distribution. So for that there is a kind of analogous function in R which is called pt instead of p-norm, okay? And we will feed it our observed t-value, t observed, as the first argument. And another important parameter of this t-distribution is actually the so-called degrees of freedom. Okay, degrees of freedom is actually nothing else than n minus 1. So if our n was 30, then the degrees of freedom will be minus 1. So that's how the degrees of freedom are typically computed for the t-test. So it's just going to be the sample size minus 1. So if your sample is size 5, the degrees of freedom will be 4. If your sample size is 100, your degrees of freedom will be 99. And likewise in this case, our degrees of freedom is equal to 29. And so just recall that, you know, if we have a t-distribution, then the 0 is actually here. So everything here is positive and everything here to the left is negative. And we see that our observed t-value is positive, so it's probably somewhere here, not on the left side, but somewhere on the right side. And that is why we will we will need to compute the area right to it. So we, again, just like for p norm, we'll have to specify lower tail equals false. Otherwise, it would compute the area to the left of this observed t-value, but we want the area to the right of it. Okay, so lower tail false. And the last step, just like for the z-test we saw previously, is to multiply this whole thing by 2 for the simple reason that we also have this area to the left, which we also consider. And we can compute that. And now we see an interesting result, actually, namely that our p-value, that is now our p-value for the t-test, is 0.13, which is, well, this is greater than 0.05, and therefore here we would have to conclude that the difference is not significant, okay? Because our p-value is larger than our threshold of 0.05. So this might come as a small surprise maybe, because previously we did a z-test and then we found that the result should be significant. Now we see that it is not significant. Well, the difference comes about due to the reason that here for the t-test we can't use the knowledge that we know the population standard deviation. And the population standard deviation we assumed previously for the z-test was 15, which is quite small. But here we can only rely on the sample standard deviation as an estimate of the standard deviation of the population. And this in our sample happens to be quite big actually. So this is 25. So you can see how this being in the denominator of the t observed value equation will make the t-value rather small. So that's why in our example here, applying the t-test and not having any knowledge about the population standard deviation will actually lead to a non-significance result in this case, okay? So that's also something to keep in mind. Depending on which test you apply, the result might of course differ. The good news is in R we actually have a simpler way that we can apply the t-test to our data, because there is actually an inbuilt function called t.test. So we might as well use that instead of like doing all these steps by hand, okay? And so I'm just going to show you how the same t-test would work when we're using this inbuilt function. So how this works is we will give this t.test function our data, in that case our sample as the first argument, so that's going to be up sample 1, and then it will take a few further arguments. For example, it wants to know what the population mean is according to the null hypothesis, so in our case that's 100, okay? It's already specified up there actually, we could just write mu is equal to mu. And it also wants to know what the significance level is at which we want to evaluate the test, in this case 0.05. We are conducting a so-called one sample t-test, so we have to specify type and then in quotation marks one sample. And lastly, another argument is that we want to compute a two-sided test, so that's what we can specify using the argument alternative, and we give it the value two-sided, again as a string, okay? Now with that we can in principle just press enter, and we see here a nice summary of the result of our t-test. So we can break this down bit by bit. So we see here our t-value, which is the same as the one that we had calculated by hand, our observed t-value, okay? We see here our degrees of freedom indeed is 29, no surprise here, it's just the sample size minus 1. And we also see the p-value, which is again matching up with what we had already figured out by doing it manually. It's something like 0.133. And so the morale of the story is that the result is not significant, right? Because this p-value is not under our threshold of 0.05. Here's a quick summary on when to use the t-test. So the t-test is useful exactly in those cases where we have a continuous dependent variable, right? So in our example, we had IQ scores. These are numbers, like it could be 101, 98, 120, 87 or something, right? So these are continuous variable. It's a continuous variable, as opposed to, for example, a categorical variable like nationality, right? So IQ scores, or in cognitive science and psycholinguistics, we could have reading times or reaction times more generally. These are measured in milliseconds, and that's also a numerical dV. And the idea is the t-test takes a numerical dV, and then you compare means between conditions. For example, you could compare the mean in one experimental condition against that of another experimental condition. Or, as in the example we just saw with the IQ scores, we didn't compare two experimental conditions and their means, but we only had one condition, you could say, one sample, namely the Uni Potsdam students, and we compared their mean against the already known population mean, mu, which was 100. In order to learn more about the different variants of the t-test, which you've surely covered in last semester's course, Statistical Data Analysis 1, I'd suggest you maybe revisit the materials from Stats 1, or you could also check again Chapter 2 of the textbook by Vasisht and colleagues, which you can find on vasisht.github.io/frec, like frequentist underscore cog sci, right? Check chapter 2 there again in order to refresh your knowledge of variants of the t-test. So for example, we just did an example with IQ scores, which was a one sample t-test. But there is also, maybe you remember, the two sample t-test, right? That would be the case where you compare two experimental conditions. And of the two sample t-test, you also have two versions depending on the use case. You have the unpaired two sample t-test and the paired two sample t-test, right? So if you want to explore these details again, please refer to the last semester's courses materials, and also to the textbook where it's all explained in very much detail. Okay, so what we've seen so far is how to conduct a t-test, and we saw this on the example of a one sample t-test in particular. Now, the next idea would be to remind ourselves how we can compute the statistical power prospectively for a t-test we want to conduct on an experiment that we are planning, right? And so that's the topic of power analysis, in this case for the t-test, okay? And so recall that the idea of statistical power is basically asking the question, under the assumption that my alternative hypothesis is true, is real, like there is in fact a difference that I'm interested in, be it like in IQ scores or reading times or anything. If that's true, like if the null hypothesis is actually false in the real world, under this assumption, how likely am I to detect this real difference applying my statistical test, in this case the t-test, given a certain sample size that I have available, given a certain effect size, and so on, okay? So that's something that you can always do prospectively only, like you can do a power analysis based on some assumptions about an experiment, about data you're going to collect in the future, right? So let's imagine the following situation. Let's say we are studying traffic in Germany, and like car-driven traffic in particular. And let's assume that it's like public knowledge or like a well-established fact that cars entering the city of Berlin from the highway, from the Autobahn, travel at a speed of 60 kilometers per hour on average, okay? And so that's our, we could say, like population mean that is known. And now what we want to compare this to in our study that we are maybe planning to do is that we want to see if that is the same for cars entering the city of Hamburg, okay? So that's something that's not established yet, let's say. I'll make this a bit prettier. And we want to test this by measuring cars that in fact enter Hamburg and measuring their speed, and then see what average speed comes out and if this is different or not from the average speed of cars entering Berlin. Now, further, let's assume we have actually already conducted a small pilot study. Let's say we've already collected some preliminary data just as a check basically that everything works, and we have already a pilot data set which is actually, well, let's say not so small, so it's actually has a rather decent sample size of 100 subjects. So the subjects would be the cars entering Hamburg in this case. So we've already collected a sample of 100 cars entering Hamburg, and we can compute the sample mean of this sample. We can compute the sample standard deviation, which is an estimate for the population standard deviation, and we obviously also have the information how big our sample is. And now the question we are asking is, given that we have these estimates, can we use them in order to conduct a power analysis, a prospective power analysis for an experiment that we want to do with a bigger sample size, in order to see what kind of sample size we actually need of like cars that we have to, whose speed we have to check while they enter Hamburg, in order to have a satisfactory likelihood that we in fact will find a true difference if it really exists. So we are back in our studio, and it turns out that we actually have this data, this pilot data from cars entering Hamburg and their measured speeds available as a data file. The data file is called carshb.txt, and we have it stored in a subfolder called data. Okay, so I'm just going to wrap quotes around this, and then we want to read this in using the read CSV command with the additional argument sep empty string, and we want to save this in the variable carshb. You can also find this data file on the Moodle, by the way. It comes together with the lecture notes, so in case you want to reproduce these analyses that will follow, you can just do so on your own computer. So we have loaded this. We can inspect how this data file looks like. So it has two columns, the column car ID, which is just, an identifier for each car, and the column speed, which measures, the speed of these cars. And we can compute what the mean of the speeds is. So that is 70, and the standard deviation in this sample is 46, okay? And so now for the power analysis, we look at this sample mean for the sample of cars entering Hamburg, and we think of what is the difference between this sample mean of this pilot data of cars entering Hamburg compared to the already well-established, well-known population mean for cars entering Berlin, which was 60. And we assume that this is the real difference. Like, that's the assumption that will go into our power analysis, is that in fact the you could call it delta. Delta is like a parameter that can mean difference typically. The difference, the real difference between speed of cars entering Hamburg and speed of cars entering Berlin is in fact, for our analysis, we assume that, is in fact this mean that we see in our pilot sample for the Hamburg cars minus the already well-established mean for the Berlin car population, which was 60, okay? So delta in this case, delta is 10.94 something, difference in kilometers per hour, that is. And another thing is, of course, the standard deviation, which we assume to be the true standard deviation of population of cars entering Hamburg. Our best guess for it is, of course, the one that we can measure in our sample. Obviously, it won't be exactly the truth, but for the power analysis, we have to make certain assumptions, like there's no way around it. So for our power analysis, just for the sake of it, we will assume that the standard deviation is in fact equal to the sample standard deviation that we could measure here. So we'll set this to be equal to that, and that is 46, as we also saw here. And now we are ready to run our power analysis. This can work here using an inbuilt function called power.t.test. Okay, we're gonna just do this with this inbuilt function here in this video lecture. In the lecture notes, you can also find a more bare bones approach where we use simulation to compute the power here. But here, for our purposes, we can just use the power.t.test function, and we'll get to data simulation for power analysis in a later video lecture in this course. The nice thing about this power.t.test function is that you can ask different kinds of question using that function. So one question you can ask is what power will I get with sample size 100, let's say? So you can specify a specific sample size and say, if I were to repeat an experiment given these assumptions, what is the power that I can expect? In other words, what is the likelihood to find a real difference with a statistical test if it is really there in the real world, okay? But we can also ask a question like, what sample size will I need to reach a power of 0.8 or 80%, which is usually deemed to be like conventionally satisfactory level threshold for power, okay? So less than 80% is really not so good, but at least 80% or higher is really desirable. And we can ask the question either this way or either this way. So let's start with that one, but then we can also see how we can ask the second question. So for the first question, we use the power.t.test function as follows. We will specify our planned sample size for the new experiment. Let's say we do again an experiment with just 100 cars, and we say that the delta, like the difference we assume to be real, is equal to what we had computed here, so 10.9, which is stored in the variable delta. The standard deviation is assumed to be 46. And again, we have to specify certain things similar as for the t-test function, that we're doing a one sample t-test, and that we are assuming that we would run a two-sided hypothesis test. So the alternative, let me write this here maybe, the alternative is two-sided. Oh, what did I do now? Two-sided. And once we run this, we can see our result here. So this power analysis is telling us if we were to do this, like run another experiment under the assumption that these are the effect sizes and variance sizes we're dealing with, then we would only find this real difference in 64% of the cases. So power would be 0.64, aka 64%. Which is not so satisfactory. It's not super bad, but as we said, like a nice minimum kind of power we would like to reach is like in the ballpark of at least 80%. Okay, so now we get the information that with a sample size of 100, we'll just get 64% power. So now we can try to ask this kind of question, which flips it around and says, we want to meet a specific power threshold. What can we do? Like, how many cars we will need to observe entering Hamburg and measure their speed in order to reach this power, given our assumptions. So in order to do that, we'll just have to modify this function slightly. So now instead of specifying the sample size n, we'll leave that actually unspecified, and instead specify our desired power, in this case 0.8, okay? And once we run this, we get the following result, namely that in order to reach a power of 80%, aka 0.8, we will need to collect at least 144.0061 cars. Obviously, we can't collect a like fraction of a car, so just to be sure, we would have to say, in order to get a power higher than 80%, we'll have to observe at least 145 cars, okay? So these kinds of questions we can ask using the power.t.test function as a way to conduct a quick power analysis in order to see how likely we're going to find a real effect in a data set that we are about to collect. All right, so we've seen how to conduct simple hypothesis tests using the t-test, and also how to estimate prospective power for an experiment that should be analyzed using a t-test. All very well, but remember that I said in the beginning that we are not only using statistics to conduct hypothesis tests, but also in order to be able to understand the generative process behind some data we are analyzing, okay? And this kind of application of statistics and what kind of models or tests we can use to accomplish that is what we are going to look at now, okay? So how to understand the generative process behind some data. So as a new mock example, let's say we go to 100 students, could be of Uni Potsdam or wherever, and we give them some psychological questionnaire which is supposed to measure their happiness, and then it will give us a measure, like a simple score, numerical score, which quantifies their degree of happiness, okay? And now let's say we've already done this. This is obviously not real data, but let's assume it was, okay? We could plot this distribution of the happiness scores here. So you see there are 100 students, so 100 of these small dots on this graphic here. And this y value is supposed to be this whatever metric we are using, okay? So the happiness score can range here from 300 something to about 800. So these are like the very happy people, these are the rather sad ones. Now, if I were to compute the sample mean and the sample standard deviation from this particular sample of happiness scores from students, I would get the following values. I've done this already in R, so I'm just writing down the results here for exactly this sample. I will get a average, like sample mean happiness score of 611 and a standard deviation of 100, more or less, okay? Now, remember that the sample mean and the sample standard deviation are also estimands of the true population parameters. That is, they are approximations, the best guess we have basically, as to what the real population parameter is for the mean of the happiness scores in the population, which we denote as mu typically, and the real true standard deviation of the happiness scores in the population, which we would denote as sigma. Now, when we visualize these data using a different kind of plot, namely a density plot, this will look as follows. So here we see the same data visualized using a density plot. That is, we can see where the density of the happiness scores is higher, like where there are many of them, like on which parts of the scale of the happiness score. So we see like around 600 roughly, we see that there's like the highest concentration of students that have a happiness score in that ballpark, whereas like on the tails of this distribution, there are fewer of them. And now this, I mean, it doesn't look like a perfect smooth normal distribution, right? It's kind of a bit more bumpy, but we can see that like if we were trying to understand from what kind of data generative process these happiness scores come from, a very useful first approximation would be to assume that they come from a normal distribution which has a mean of 611, because that's our best guess for the true population parameter. That's our sample mean, okay? And a population standard deviation of 100, okay? So we can make this assumption, like we can put this out as a possible model of happiness scores, of how happiness scores are generated, quote unquote. We could say happiness scores are normally distributed in the population with a population mean of 611 and population standard deviation of 100. So we would assume that there's like this true distribution, which is a perfect normal distribution with a mean 611, which looks maybe somewhat like this. And even though this true normal distribution that we are assuming here is like not exactly matching up with the density that we find in this particular sample, this sample could have very plausibly been generated from this true distribution, like this kind of green color line here that I've just drawn, because it's already pretty close to, like our sample density plot already looks pretty much close to how the true distribution that we are assuming here as the true data generative process looks like, okay? So that seems like a very reasonable way to try to model how these data are generated. All right, so we just saw this example of these happiness scores from the sample of 100 students, which turned out to be distributed in such a way that we can approximate the generative process using this normal distribution with mean 611 and standard deviation 100. Now, let's say we gave these same 100 students a different questionnaire also, which is not measuring happiness, but instead is measuring anxiety, okay? So maybe there is some aggregate anxiety score based on the responses that these students give. And now it could be interesting to see how these like anxiety scores are distributed. So in order to have an impression of that, I'll maybe first delete these numbers here, which are related to the happiness score. And now we can see how the scatter plot for the anxiety values looks like. So it looks like this. And we can see here on the y-axis we have the anxiety scores, which range from 0 to 1000 here. The label is kind of odd here, but never mind, these are the anxiety scores. And here on the x-axis we have the 100 different participants of this test. And here maybe we can notice something interesting about the distribution. Like it's not so visible here, but maybe in the next plot, namely that there is like a big kind of cluster of people on these lower ends of the anxiety score, like from maybe 0 to, let's say, 400 or 500. And then there seems to be like another bunch of people, but like fewer of them, that are spread more on the edges of this scale, okay? So like more on the higher end, from ranging from 500, 600 up until 1000 and more. So it's still true that we can, of course, compute the sample mean and the sample standard deviation from this as we do for any sample. So in this case, I've also pre-calculated this in R, and it turns out that the result here is in fact 300 204 more or less for the sample mean, and 290 for the sample standard deviation. But here there is a crucial point, namely that when we look at the other plot, which is the density plot, we see that this can't really be a normal distribution, right? For a normal distribution, which would have a mean of 304 and a standard deviation of 290, we would expect the curve to look really much more symmetrical. So we would expect maybe something like this or so. But here we see that this actual curve that we get, it has like a very far right tail. It has like these bumps to the right. So it's really not symmetrical around the mean of the sample, which suggests that probably in this case for the anxiety scores, the true generative process is not a normal distribution, and therefore we can't really assume that these sample means and sample standard deviations in this case will be a good approximation as population parameters for a normally distributed population of scores, because here probably the true distribution is maybe something else. Maybe it's a mixture of multiple normal distributions with one mean being here and another one being slightly more to the right, or it could maybe be log normal distribution, which is also a known kind of skewed distribution. So we don't really know. We could try different things and see which distribution looks most like this one in terms of its shape, and then it could be a good approximation. But at least we see here, as opposed to the other example with the happiness scores, that the normal distribution is probably not a good way to explain these data, because the normal distribution assumes the symmetric distribution, roughly like I've sketched here, and not this huge bump on the right and this long tail to the right. So that's something we can see here just by visualizing this density plot. When thinking about data generation processes, it is sometimes also useful to try to understand the relationship between two variables. And a simple example of this is what you surely remember, simple linear regression. And we're going to see or review how this works. So let's say we are a researcher and we are studying something in psychology. For example, it could be that we have a population of students, again, because why not? And we have two different measures that we obtain from them, numerical measures. So one is a measure of stress, like the stress level. And another measure is if they have some pathological, psychological symptoms. So I'm just going to call this psychological symptoms. And now let's say both of these are just as we said, just continuous variables, okay? And now we could have the hypothesis, quite plausible, I guess, that the stress level influences the degree to which students show psychological symptoms, so that there is some relationship between the stress level on the one hand and the psychological symptoms on the other hand. And for example, we could, if we assume that this is causally related like this, we could say for our analysis that this is our dependent variable and this is our predictor. So we try to predict the degree to which a student has psychological symptoms or issues by the amount of stress they experience or they're exposed to, okay? Well, a suitable model in order to try to capture this relationship, assuming it is a linear relationship, is a simple linear regression model, okay? And if we give these two variables somewhat more handy, tractable names, we could also say this is the variable x is the stress level, our predictor, and our dependent variable, the psychological symptom score, is our variable y, let's say. So with the specification of these two variables as such, we can basically say that mathematically, the kind of relationship we want to find here is that the psychological symptom score for any particular participant I, so this is just an index for a specific participant, should be represented by alpha, which is the intercept, plus beta, which is the slope of the linear relation, times xi, in other words, the stress level score of this particular participant, plus epsilon, which is residual, which is the residual variance which is not explained by this relationship, okay? And so the two parameters that we have to estimate in this model are alpha and beta, where, as I just said, alpha is what we also call the intercept and beta is the slope. And so the idea, that's the whole point of linear regression, is to find the best values for these two parameters. So we could obviously pick many different numbers and plug them into this equation, but the point is we want to find the optimal alpha and beta, like the optimal intercept and slope, in such a way that by picking those two, we will minimize the residuals. More specifically, we will minimize the sum of squared residuals. Like if we sum the residual, like the square of the residual for each of the participants, like we take participant 1 and take the square of the residual, and then participant 2 and then participant 3, we take the sum of all of this, and we want to find the perfect alpha and beta in such a way that the sum of squared residuals is as small as possible. So in other words, the amount of variance that is left unexplained by the model should be as small as possible. And all this is basically just another way of saying if we plot this visually with our variable x here and our variable y here, and these are all the data points that we have collected, we want to find the best fitting line that goes through these points, right? So maybe here the best fitting line looks like this. And so best fitting means that, well, the sum of squared residuals is minimized, and a residual here, just as an example for this data point, would be how far it is away from this best fitting line, okay? Or this data point is this far away. This one is a bit closer to the best fitting line. And if we sum all of these together, or well, actually they're squares, then we want to find the line that goes most smoothly through these points, because the residuals are as small as possible, okay? And here, beta, the slope, basically describes how steep the line is. So if beta is very large, the line would be a bit steeper. If it's smaller, it's less steep, or if it's negative, it would actually be a decreasing line. And alpha describes the point at which this line crosses the y-axis. So in other words, where x is 0. So here, x is 0, that's the y-axis. And let's say if the value here for y would be 1, just as an example, then alpha would have the value 1. So that is how we can see the intercept in such a plot. Okay, so next let's see this particular example with these psychological data in R, where we can load this data set and then see how we can compute a linear regression model. All right, so let's go back to RStudio, and now we can load this data file containing the data set with these measurements we just talked about, namely the stress levels and the psychological symptoms, into R. And you can also actually find the data file on the Moodle. It comes together with the lecture notes in case you want to reproduce the next steps yourself in your own version of R. So we'll use the read table function, and in fact the data set is stored in a subfolder called data, and the data file has the name stresssymptoms.txt. We'll load it with a header equals true argument, and that's it. So now it's stored in a variable called stresssymt. Okay, we can maybe visualize the first couple of lines of this data set just to get an impression of how it looks like. So we see that there is a column participant, which supposedly contains these participant indices. We have a column stress, which collects these stress level measurements, and we have these psychological symptoms in this column here. We can also maybe see with n-row how many entries this dataset has. So in fact 107, so there are 107 participants overall in this sample. Now, what we can do is, first we can visualize this relationship, like without running any model, basically doing this kind of scatter plot that I just showed you conceptually. So the way to do this would be simply we can use the plot function, the core like base R function plot, and we give it now stress symptoms. Dollar means, we want to access a particular column, and we want to have our y-axis specified as symptoms, and that we want to plot as a function of stress. Okay, so stress, symptoms, stress. Okay, so let's run this and make some space here on the right so we can see our plot. And once we press enter, we can see this relationship here. So on the x-axis we have the stress levels, and on the y-axis we have our dependent variable, namely the psychological symptoms. Like we can even make this a little bit bigger in a separate window. I'll just bring it over here. So just to have a nice view of it, we can see how these data are distributed. So we can imagine that the best fitting line, like if we imagine how this would look like, would probably be something like that, okay, but should be obviously a straight line. And but to really find the best fitting line, we will obviously need to run this linear regression. This will find us the optimal slope and intercept parameters for the best fitting line for these data. Now, a tangential problem that we will see later in this course is how to deal with outliers. For example, this point is really far off from the rest of the distribution, or also this point or that point. And these kinds of outliers become problematic because they can heavily influence the slope and the intercept of the model. So maybe we have to treat them separately or like exclude them because maybe these data points are really implausible and are just like an artifact of measurement error, or like some participant not really properly filling out the questionnaire. So that's a whole topic of its own, like how to deal with outliers, and that's something we will come back to later in this course. But for now, let's ignore this and just fit the best fitting line here. All right, let's now quickly revise how we can run the linear regression model on these data in order to find the best slope and intercept for this problem. So we can do this using the LM function, LM like linear model, and we're gonna specify the dependent variable. In our case, this is symptoms. This should be predicted by stress, and we give the argument data, which is our data set stress symptoms. And once we run this, we could actually first maybe save it in a variable, this model, maybe variable M1. And if we write M1, we can in fact see the result of this linear regression. So in this case, we see that the intercept the model found should be 74, more or less. And the slope, like the parameter beta, should be positive 0.78, okay? So it's a mild positive relationship because the slope is positive. So more stress means more psychological symptoms. And in other words, for each unit of stress, like for each step of 1 on the unit of stress, there is a 0.78 unit increase in the score of the psychological symptoms measure. All right, so this is everything for the first introduction or recap lecture. All of this should really not be news to you because this is all just topics that you've covered last semester in Statistical Data Analysis 1. Nevertheless, it's good to revise all of this so we are all on the same page and that we can move on to more advanced topics starting next week. So see you then.